the rules of optimization with derivatives. So the rules of optimization with derivatives. First, we'll understand the rules and then I'll come back to the problem. So we have already discussed key rules of differentiation, that is power rule, sum difference rule, product rule, quotient rule, chain rule. Today we will discuss the steps for optimization problems. So first we will express fx in simplest form. So fx is explained in simplest form, the function fx in simplest of terms. Next step, we have to calculate f dash x or the first derivative and then solve f dash x is equal to 0 to find critical numbers, which is potential maximum or minimum. To find critical numbers represented by C, which are potential, maximum or minimum. Next, we have to test these critical points. Then we use the second derivative test. Second derivative test. Now what is second derivative test? If f double dash c is less than 0, then it is local maximum. Local maximum. If f double dash c is greater than 0, then it is local minimum. Next, the first derivative test. We have to check sign changes around c. Positive to negative means maximum and negative to positive means minimum. Last, evaluate fx at the boundaries of the feasible domain, as the absolute extremum might occur there. Now let's come back to the problem. A rectangular cake dish is made by cutting out squares from the corners of a 25 cm by 40 cm rectangle of tin plate and then folding the metal to form the container. What size squares must be cut out to produce the cake dish of maximum volume? Now let me erase the rules. So how do we solve? So this is the given rectangle. Now we draw the figure of rectangular cake dish, which is made by cutting out squares from the corners of this rectangle, which is 25 cm by 40 cm dimension. So we just draw a rough sketch. Please note it is not drawn to scale. Now, x centimeter is the side length of the squares that are cut out. So all these are x. Now, this is the original rectangle. I'm just using dotted lines to fill in the space. Now we note that the side lengths are 25 centimeter by 40 centimeter. So, sorry, there's a mistake here. This is not x. We have to find the length of this part. So if the side length is 25 cm here, then the value here is 25 minus 2x centimeter, and here it is 40 minus 2xy, because this is x and this is x, and here also this is x. So this part is 40 minus 2x centimeter. The length is 40 minus 2x centimeter, this part. Now we will calculate the volume. Volume is equal to length multiplied by breadth multiplied by depth. Now we put in the values. Length 40 minus 2x multiplied by breadth, which is 25 minus 2x, multiplied by depth, which is x. Now simplifying, we multiply these two first. So 40 multiplied by 25 is 1000, minus 40 multiplied by minus 2x is minus 80x. Again, minus 2x multiplied by 25 is minus 50x. Minus 2x multiplied by minus 2x is plus 4x square multiplied by x. Now simplifying further, we get 1000x minus 80x square minus 50x square plus 4x cube. Now we again simplify it further. So 1000x minus, so 80 plus 50 is 130x square plus 4x cube, cm cube, the unit of volume. Now x is greater than 0 because it is the side length of the square. So this cannot be a negative value. And 25 minus 2x is also greater than 0. So what do we get? Simplifying here, we get 25 is greater than 2x and x is less than 25 by 2, which is 12.5. So x lies between the domains x greater than 0 and less than 12.5. Now the first derivative test. I will erase this part. First derivative test. What do we observe? That we know that volume, so fx or dv, fv is, as I solved previously, 1000x minus 130x square plus 4x cube. This is the expression for volume. So the first derivative test, so dv by dx is, now if you simplify from here, I am simplifying from the last part. So 12x square minus 130 multiplied by 2 is 260x plus derivative of 1000x is plus 1000. If you simplify, we get, taking out common factor, which is 4. So we get 4 within bracket 3x square minus 65x plus 250. Now factorizing this expression, what do we get? 4, 3x multiplied by 3x minus 50 multiplied by x minus 5. Now, we know the rule for first derivative test that we have to solve f dash x is equal to 0 to find critical numbers in order to find out the potential maximum or minimum. So, dv by dx is equal to 0 when 3x minus 50 is 0 or x minus 5 is equal to 0. So this means here x is equal to 50 by 3, which is 16, 2 by 3 in mixed fraction, or x is equal to 5. Now we will find out the second derivative test. Now the second derivative test. The second derivative test is if f double dash v or d2v by dx square is less than 0 or greater than 0, but it is already mentioned that we have to find the size of squares which must be cut to produce the cake dish of maximum volume. So local maximum is occurring when f double dash v is less than 0. So let's find out d2v by dx square. Okay, so earlier we found out that the critical values C were 16, 2 by 3 and 5. So we will take this value 5 and solve. So here again dv by dx, we had calculated it to be 4 3x minus 50 multiplied by x minus 5. So this follows d2v by dx square. The second derivative d2v by dx square is from the first expression, which is now dv by dx here is 12x square minus 260x plus 1000. This will simplify my calculation. That is why I've come up to this part. So d2v by dx square from this part is 24x minus 260. So when x is equal to 5, what do we observe? d2v by dx square is 24 multiplied by 5 minus 260. Now 120 minus 260. So the value is minus 140, which is less than 0. So the shape of the curve is concave down. Concave down. And we have a local maximum. Because the value is less than 0. So the maximum volume is obtained when maximum volume is obtained when x is equal to 5, which is when 5 centimeter squares are cut from the corners. So the size length of the square is x is equal to 5 centimeter. So that's it for today's lesson. So what did we learn? That optimization using derivatives help us find the best possible solutions to real life problems. By identifying maximum and minimum values, we can solve questions related to profit, cost, distance, area, and efficiency with confidence. With regular practice, optimization problems become logical, interesting, and easy to solve. See you in the next lesson video. Till then, happy learning. Welcome back, everyone. Have you ever wondered how fast an exponential function like ex, e to the power x, grows, or how the logarithmic curve ln x changes as x increases? In today's lesson, we'll explore the derivatives of exponential and logarithmic functions, the powerful tools that help us understand their rates of change. So let's begin exploring and solve few sums also. But first, let's explore the various functions and its derivative or rate of change. So the function fx and its derivative is f dash x. Today we will discuss just e to the power x and ln x, just these two functions. And in the next lesson, we'll discuss about the derivatives of trigonometric functions. So let's begin. If function is e to the power x, then its derivative is unchanged. It is e to the power x. If function is e to the power fx, then by chain rule, its derivative is e to the power fx multiplied by f dash x. If the function is ln x, then its derivative is 1 by x. And if the function is ln fx, then its derivative is f dash x by fx, and this is also by chain rule. So let's begin solving few sums today. Just give me a moment to erase. So the first problem, find the gradient function for y is equal to, find the gradient function for y is equal to 1 by root under 2 multiplied by e to the power minus x plus 1. So let's begin solving. Now we rewrite this as y is equal to 2 e to the power minus x plus 1 whole to the power minus half. Now we can also write this as y is equal to u to the power minus half, where u is equal to 2 e to the power minus x plus 1. Now we know that dy by dx can be written as dy by du multiplied by du by dx. So we continue solving here. What do we get? Dy by du is equal to, from here, minus half u to the power minus half minus 1. So which means dy by du is equal to minus half u to the power minus 3 by 2. And from here, du by dx is equal to Now we'll use the chain rule. So e to the power minus x multiplied by 2, this is unchanged, 2e to the power minus x and multiplied by minus 1. Okay, so yes, now we come back here. So du by dx, dy by dx is equal to dy by du is minus half u to the power minus 3 by 2 multiplied by du by dx, which is 2e to the power minus x multiplied by minus 1. Now what do we get? We substitute the value of u here. So also we observe that 2 and 2 we can strike off, and minus 1 into minus 1 is 1. So we simply first we substitute the value of u here. The terms are 2e to the power minus x plus 1 whole to the power minus 3 by 2 and multiplied by e to the power minus x. So this is my final answer. Dy by dx is 2e to the power minus x plus 1 whole to the power minus 3 by 2 multiplied by e to the power minus x. Now let me solve another sum involving logarithmic function and finding its derivative. Just give me a minute. So find the gradient function for y is equal to ln x e to the power minus x. Now what do we observe here? That y is equal to ln x plus ln e to the power minus x. Now what rule are we using here? This is the logarithmic rule. ln ab is equal to ln a plus ln b. Also y is equal to ln x minus x, y ln e to the power a is a. We are using this rule. We know that the base of ln logarithmic function is e. So ln e base e to the power a is a. Now we find out the derivative. So dy by dx is equal to ln x, the derivative is 1 by x, and derivative of minus x is minus 1. So this is the final answer. So that's it for today's lesson. We discovered how exponential function e to the power x stands out because its derivative is same, implying continuous growth. And for logarithmic functions, their derivatives or rate of change decreases as x grows. These relationships form the bridge between growth and decay, increase and decrease, and helps us understand how change behaves in the real world. Don't forget to like, share and subscribe here for more engaging maths lessons with me.